What happens when a messenger from another star system arrives, but the world's most powerful eyes suddenly go blind? A bombshell has quietly dropped on the astronomical community. As many of the West's premier telescopes go dark, China has released the first new images of the interstellar Comet 3I Atlas. This isn't just a scientific curiosity, it's a major shift in who watches the stars and who tells their stories. Let's break down what's really happening.
Strange composition.
So, what makes this visitor from another star so bizarre? Interstellar objects are messengers from distant star systems, and 3I Atlas is only the third one we've ever confirmed. Unlike its predecessors, Oumuamua and 2I Borisov, this comet is giving us an unprecedented look at the chemistry of another solar system. Early observations from teams led by astronomers like Quanji Ye, using instruments like the James Webb Space Telescope's NIR SPEC, have revealed an unusual chemical fingerprint. The cloud of gas and dust surrounding it, called a coma, is incredibly rich in carbon dioxide, with some studies suggesting the CO2 to water ratio is more than 10 times higher than that of typical comets from our own solar system's Oort cloud, like Comet Hale-Bopp. This suggests it formed in a very different and likely much colder environment, possibly in the outer reaches of a red dwarf star system, with a nucleus estimated to be between 2 and 5 kilometers in diameter, and a hyperbolic trajectory with an eccentricity greater than 3. It's a pristine sample of the building blocks from a completely alien planetary system, delivered right to our doorstep. Every piece of data is a clue to how planets and life might form elsewhere in the galaxy, which is why every single observation is so critical.
Telescopes go dark.
Just as we were starting to unravel its secrets, the line went dead. The world's most powerful observatories, the household names of astronomy like the Hubble Space Telescope, the James Webb Space Telescope, and the European Southern Observatory's Very Large Telescope in Chile, have reportedly fallen silent in their observations of 3I Atlas. Now, this doesn't mean they're all broken. In reality, large telescopes operate on incredibly tight schedules planned in cycles months or even years in advance. Getting discretionary target of opportunity time is fiercely competitive, with thousands of proposals vying for a few precious hours of observation. These facilities also require regular, intensive maintenance to keep instruments like Hubble's Wide Field Camera 3 or the VLT's X-Shooter spectrograph running at peak performance. A combination of scheduled downtime, maintenance, and pre-booked observation blocks on other cosmic targets has created a perfect storm, a temporary but critical observational gap. For a fleeting visitor on a one-way trip out of our solar system, losing even a few weeks of observation time means permanently losing a piece of an irreplaceable puzzle.
China steps in.
But the sky is never truly silent. Someone else was listening. Into this observational vacuum, China's astronomical community stepped forward, leveraging their growing network of advanced facilities, such as the 2.16-meter telescope at Xinglong Station, part of the National Astronomical Observatories of China. They released sharp, high-resolution images of 3I Atlas. These aren't just blurry snapshots, they are deep-field images that capture the comet's evolving structure with stunning clarity. Established in 2001, the NAOC has rapidly developed world-class capabilities, driven by a national strategy to become a leader in astrophysics. Scientists like Jing Li and her colleagues are at the forefront of this effort, utilizing these modern facilities to monitor transient astronomical events. By capturing fresh frames of the comet's coma when other major facilities were dark, Chinese astronomers didn't just fill a gap. They seized a moment of scientific leadership. The timing was impeccable, demonstrating that years of heavy investment outlined in their 5-year plans have paid off, positioning them to make critical contributions right when they matter most.
Data controls narrative.
Here's the bottom line. Whoever has the data writes the first draft of history. In science, the teams that publish first often shape the entire conversation around a discovery. By releasing the only new images of 3I Atlas during this critical window, Chinese observatories gain immense influence over the scientific narrative. Think about how the first close-up images of Pluto from the New Horizons mission, released by Alan Stern's team, completely defined our perception of that world for years. Their images might highlight specific features, a new jet of gas, a change in the dust plume, or a brightening event, that will guide all subsequent research. A first discovery paper on a major object can garner thousands of citations, solidifying the author's place in scientific history and influencing future funding decisions. This puts their interpretations at the center of the debate and makes their facilities the go-to source for the next chapter of this comet story. They are now in a prime position to lead the charge on developing the definitive models that explain the comet's origin and behavior, potentially defining our understanding of this object for generations.
Data sovereignty.
This isn't just about science, it's about control. For decades, Western astronomy has largely operated under a philosophy of open data, with archives like NASA's MAST providing public access. But that's not the only model. For example, data from the European Southern Observatory often has a one-year proprietary period for the observing team before it becomes public. As different nations become major players, the question of data access becomes more complex. The decision to release or withhold data can become a powerful tool of soft power. If China's new images and follow-up data are shared openly, it could foster a new era of global collaboration. However, if access is controlled through institutional channels, it could complicate independent verification and sideline researchers from other countries who lack the right connections. This situation brings up serious questions about scientific sovereignty and the norms of data sharing. Who owns data from the cosmos? How that question gets answered will determine whether the future of astronomy is more collaborative or more fragmented and competitive.
National prestige.
Look, space has always been a stage for national power. From the space race to the latest Mars missions, scientific achievements are deeply intertwined with national pride and geopolitical influence. China has been transparent about its ambition to become a space superpower, investing over $13 billion annually into its programs. These efforts include the successful Chang'e lunar sample return missions, the construction of the permanent Tiangong space station, and the development of the Suntian space telescope, designed to rival Hubble. Releasing pivotal images of a rare interstellar comet at the exact moment Western telescopes are offline is a massive public relations victory. It sends a clear message to the world: Tranin pasin so ban josar, Tranin golan doting ninensam, Adens drijers. Not Tranintan just catching up. It is a leader in frontier science with the technical prowess to deliver when others can't. The narrative that China saved the day by ensuring continuous observation of this visitor resonates far beyond scientific journals, bolstering its image as a global technological powerhouse capable of leading humanity's exploration of the cosmos.
Infrastructure fragility.
What does it say when the world's most powerful eyes can all blink at once? This episode, honestly, serves as a stark reminder of the fragility of our global astronomy infrastructure. The catastrophic 2020 collapse of the 305-meter Arecibo Observatory is a perfect example of how the loss of a single, unique facility can leave a massive gap in our scientific capabilities for years. For decades, the community has relied heavily on just a handful of flagship observatories. While these telescopes are incredibly powerful, this centralization creates a single point of failure. Funding cycles, maintenance, or technical issues can, take multiple key instruments offline simultaneously. The 3I/Atlas event proves this model is unsustainable for time-sensitive science. It highlights an urgent need for a more diversified and distributed global network, something the upcoming Vera C. Rubin Observatory in Chile will help address with its continuous sky survey. Relying on a few titans is a risky bet when the universe doesn't wait for our schedules, and a single nation with agile facilities can now step in and dominate a major discovery.
Verification questions.
Just because we have new pictures doesn't mean we have the full picture. This is where, honestly, a healthy dose of skepticism comes in. While the new Chinese images are invaluable, they raise some pretty critical questions for the global scientific community. Are these images calibrated in a way that is fully compatible with data from other observatories? For the science to be robust, the global community needs full and timely access to the raw FITS files, the standard format for astronomical data, along with detailed metadata. This is really essential for independent analysis using standard software tools like AstroPy. It's also crucial that the astrometric data, the precise position of the comet, is submitted to the Minor Planet Center for independent orbital calculations, which require precision down to a fraction of an arcsecond. There's also a real danger of over-interpreting limited data. Without concurrent spectroscopic observations to analyze its chemical composition, any conclusions about the comet's activity could be biased or incomplete. Transparency will be key to ensuring these observations become a trusted part of the scientific record.
What the images reveal.
So, what are the Chinese observatories actually seeing in these new frames? The released images are more than just pretty pictures, they're actually rich with scientific data that allow for precise physical modeling. Observers are pointing to subtle but significant details, like hints of new jets of gas and dust erupting from the comet's nucleus. These jets are crucial because they produce non-gravitational forces. They act like tiny rocket thrusters that can, subtly alter the comet's path by hundreds of kilometers. Tracking these minute deviations, a specialty of astronomers like Marco Micheli, requires high-cadence astrometry from images like these. Furthermore, brightness gradients across the coma seem to be shifting, which could suggest that the outgassing is anisotropic, happening from specific active patches on the surface. By taking many images in quick succession, the Chinese teams can monitor rapid transient events that might otherwise be missed. This morphological data provides the crucial visual context needed to interpret spectral data from other observatories, past and future, becoming the scaffold upon which a complete understanding of 3I Atlas will be built.
Global wake-up call.
This isn't a story about one comet, it's really a glimpse into the future of discovery. The 3I Atlas incident is a major wake-up call for the entire astronomical community. It has exposed the weaknesses in our current observation strategies and underscored the growing multipolar nature of space science. This event will likely accelerate calls from organizations like the International Astronomical Union for more resilient, globally distributed networks like the Zwicky Transient Facility that can provide redundant, 24/7 coverage for high-priority targets. It will also force a conversation about formalizing emergency protocols, ensuring that when a rare object appears, an all-hands-on-deck observation plan can be triggered automatically across observatories in different nations. The future of astronomy can't rely on luck or the availability of a single instrument. The game is changing, and this fleeting messenger from another star has just revealed the new rules for how we play it. The story of 3I Atlas is a powerful reminder that the universe doesn't wait for anyone. A visitor from another star system is hurtling through our cosmic backyard, and for a critical moment, China's observatories were our only eyes. This event will reshape not just our understanding of this comet, but the future of how humanity watches the skies. What are your thoughts on this shift in the cosmos? Let us know in the comments below. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the future of technology and space. Thank you for watching Sci&Y. When NASA's computers started receiving impossible data from the edge of our solar system, scientists couldn't believe what they were seeing. After 47 years of silent travel through the cosmic void, Voyager 1 has transmitted discoveries that challenge everything we thought we knew about interstellar space. Today, on Sci&Y, we're unveiling the shocking revelations that have left astronomers questioning the very nature of our universe. From mysterious humming sounds to unexplained cosmic phenomena, these findings will change how we view our place in the galaxy forever. The impossible mission that defied all odds. Voyager 1 was designed to last just 5 years, yet it's still transmitting data after nearly half a century, making it humanity's most successful space mission ever. In 1977, NASA launched what seemed like a routine planetary exploration mission. Voyager 1 and its twin, Voyager 2, were built using 1970s technology with computer systems containing just 70 kilobytes of memory, less than a single smartphone photo today. Originally designed to study Jupiter and Saturn during a rare planetary alignment, these spacecraft were expected to go silent by 1982. Instead, they embarked on humanity's greatest journey into the unknown. The mission capitalized on a once-in-176-year gravitational alignment that allowed the spacecraft to use planetary gravity as cosmic slingshots, accelerating them toward the outer solar system. What began as a 5-year mission has become a 47-year odyssey that redefined our understanding of space. Today, Voyager 1 travels at 38,000 miles per hour through interstellar space, sending back data from regions no human-made object has ever explored. The fact that this 1970s technology continues functioning in the harsh environment of deep space represents one of engineering's greatest triumphs. Crossing the final frontier into interstellar space. On August 25, 2012, Voyager 1 became the first human-made object to leave our solar system, entering a realm where the sun's influence ends and true interstellar space begins. The moment Voyager 1 crossed the heliopause, the boundary between our solar system and interstellar space, marked a historic milestone for humanity. At 11 billion miles from the sun, the spacecraft detected a dramatic change in its environment. The solar wind, a stream of charged particles flowing from our star, suddenly dropped to nearly zero, while cosmic radiation increased threefold. This transition wasn't gradual, it was like stepping from a protected harbor into an open ocean. The heliopause acts as our solar system's shield, protecting us from the galaxy's intense radiation. Beyond this boundary lies the interstellar medium, a vast expanse filled with remnants from ancient star explosions, cosmic dust, and mysterious phenomena that scientists are only beginning to understand. Voyager 1's instruments detected strange magnetic field fluctuations and unexpected particle densities that contradicted existing models. The spacecraft found itself in an environment where the familiar rules of our solar system no longer applied. This crossing represented more than a technical achievement. It was humanity's first step into the galactic neighborhood, opening a new chapter in space exploration.
The mysterious humming sound from the void.
Voyager 1 detected a low, persistent humming sound in the supposed silence of interstellar space. A discovery that has scientists completely baffled about what's creating this cosmic symphony. In the vacuum of space, sound shouldn't exist. Yet Voyager 1's instruments detected something extraordinary, a continuous, low-frequency humming emanating from the interstellar medium itself. This wasn't sound as we understand it on Earth, but rather vibrations in the sparse gas and plasma that fills the space between stars. The humming appears to be generated by the interstellar medium's interaction with cosmic phenomena, creating a kind of cosmic background music that permeates our galaxy. Scientists describe it as similar to the sound of wind through trees, but occurring in a medium millions of times thinner than Earth's atmosphere. The discovery challenges our understanding of how energy propagates through space, and suggests that interstellar space is far more active than previously thought. These vibrations might be caused by stellar winds from distant stars, shockwaves from supernovae, or even more exotic phenomena we haven't yet identified. The humming varies in intensity and frequency, suggesting it responds to changes in the local interstellar environment. This cosmic soundtrack provides scientists with a new way to study the structure and dynamics of our galaxy, turning Voyager 1 into an interstellar seismograph.
The heliopause's shocking behavior.
You know, the boundary of our solar system isn't the stable barrier scientists expected. Instead, it's moving, shifting, and behaving in ways that completely contradict our models of how space works. The heliopause, which is our solar system's protective boundary, has revealed itself to be way more dynamic and unpredictable than anyone imagined. Rather than maintaining a steady position, this cosmic border actually fluctuates dramatically, sometimes moving billions of miles in relatively short periods. Data from Voyager 1 and 2 shows the heliopause exhibiting strange angles and irregular shapes that just defy current theoretical models. Back in 2014, NASA's Interstellar Boundary Explorer satellite detected unusual brightening of energetic particles, which suggested massive disturbances in the boundary region. These irregularities simply don't match existing predictions about how the solar wind should interact with interstellar space. The heliopause's movement might even explain why Voyager 1 and 2 reached interstellar space 6 years apart, even though they followed similar trajectories. Scientists have observed the boundary creating shock waves and turbulence that ripple through both the solar system and interstellar space. This dynamic behavior suggests our solar system is more like a living organism than a static structure, constantly responding to galactic forces we're only beginning to understand. The implications are pretty profound. If our solar system's boundary is this unstable, what does that mean for the protection it provides against cosmic radiation?
Electronic confusion in the cosmic deep.
So, in May 2023, Voyager 1 began transmitting garbled, incoherent data instead of scientific measurements, as if the spacecraft was suffering from electronic dementia in the depths of space. 46 years into its mission, Voyager 1 experienced what NASA engineers described as electronic aphasia. The spacecraft's attitude articulation and control system started sending random, meaningless data instead of coherent status reports. From Earth's perspective, it honestly looked like Voyager 1 was losing its ability to communicate effectively, much like how a person with aphasia struggles to form coherent sentences. The mystery deepened when engineers realized that, despite the garbled communications, Voyager 1's radio signal remained strong and stable, which meant the spacecraft was still functioning normally. Its scientific instruments just kept operating without any awareness of the communication problem, and the fault protection system, designed to put the spacecraft in safe mode during emergencies, never activated. After a lot of investigation, NASA discovered the problem. The control system had switched to a computer that had been dormant for years, basically trying to use obsolete hardware to process modern commands. The solution required sending precise instructions across 15 billion miles of space to reactivate the correct computer system. This incident really highlighted the incredible challenge of maintaining 1970s technology in the harsh environment of interstellar space, where cosmic radiation constantly bombards the spacecraft's electronic systems. Surviving the impossible, technology beyond its limits. Voyager 1's instruments should have frozen solid years ago when NASA turned off their heaters to save power, yet they continue functioning perfectly in temperatures that would destroy any other spacecraft. Honestly, the laws of physics suggest Voyager 1 should have died long ago. As the spacecraft's plutonium power source gradually decays, NASA has had to shut down non-essential systems to conserve energy. In 2019, engineers made the tough decision to turn off the heaters that keep the scientific instruments warm in the -270°F environment of space. This should have been a death sentence for the delicate electronics, yet all 5 instruments continue operating flawlessly. NASA engineers are genuinely puzzled by this phenomenon, unable to explain how 1970s technology survives in conditions that would instantly destroy modern spacecraft. The instruments operate in temperatures hundreds of degrees below their design specifications, totally defying every engineering principle. Some scientists theorize that the instruments generate just enough internal heat from their electronic operations to prevent complete freezing, while others suggest that decades of cosmic radiation exposure may have altered the materials in unexpected ways. The spacecraft's resilience has actually forced engineers to reconsider fundamental assumptions about electronics in extreme environments. This unexpected durability has extended Voyager 1's mission far beyond anyone's wildest expectations, allowing it to keep transmitting data from the interstellar frontier where no human technology has ever ventured.
The cosmic radiation bombardment.
Beyond our solar system's protective shield, Voyager 1 faces a constant barrage of cosmic radiation that's, wow, 3 times more intense than anything experienced within our cosmic neighborhood. Interstellar space has revealed itself to be a far more hostile environment than scientists ever anticipated. Once Voyager 1 crossed the heliopause, it encountered cosmic radiation levels 3 times higher than those within our solar system's protective bubble. This intense radiation, consists of high-energy particles accelerated by distant supernova, black holes, and other extreme cosmic phenomena. These particles constantly bombard the spacecraft, gradually degrading its electronic systems and creating cumulative damage that just builds over time. The radiation can actually flip individual bits in computer memory, causing small errors that accumulate into much larger problems. It's honestly like trying to maintain a complex machine while it's being continuously sandblasted by invisible particles traveling at nearly the speed of light. Despite this constant assault, Voyager 1 systems continue functioning through a combination of robust 1970s engineering and clever software workarounds developed by NASA's engineers. The spacecraft's experience provides crucial data about the radiation environment that future interstellar missions will face. Understanding these conditions is essential for designing spacecraft capable of surviving the journey to nearby star systems. Voyager 1 has become humanity's first radiation scout, mapping the dangerous terrain that lies between the stars and providing invaluable information for future deep space exploration.
Software updates across the cosmic void.
NASA engineers regularly send software updates to Voyager 1 across 15 billion miles of space, basically providing tech support to a computer system that's actually older than most of the engineers working on it. Maintaining Voyager 1 requires honestly some of the most challenging technical support in human history. The spacecraft operates with 1970s computer systems programmed in assembly language, a low-level programming code that directly controls hardware components. When problems pop up, NASA engineers have to write new software instructions and transmit them across the vast emptiness of space, where radio signals take over 22 hours just to reach the spacecraft. The engineers use a mix of assembly language and pseudocode to create efficient programs that won't overwhelm the spacecraft's limited 70-kilobyte memory. Each software update has to be perfect. There's really no chance for quick fixes or patches when your target computer is billions of miles away. These updates have solved critical problems throughout the mission, from reactivating backup systems to working around failing components. In one case, a software update saved Voyager 1 from potential disaster by activating fail-safe mechanisms when a hardware component failed. The process requires engineers to think like programmers from the 1970s, using techniques and limitations that modern computer scientists rarely ever encounter. This cosmic tech support is, honestly, one of the most impressive examples of long-distance troubleshooting ever attempted, keeping humanity's most distant ambassador operational out in the depths of interstellar space.
Revolutionary discoveries that changed everything.
Voyager 1's journey revealed that Jupiter has 3 delicate rings. Saturn's rings contain thousands of intricate braids, and volcanoes exist on moons we once thought were totally dead, completely revolutionizing our understanding of the outer solar system. Before Voyager 1's grand tour, our knowledge of the outer planets was limited to fuzzy telescope images and just basic orbital mechanics. The spacecraft's close encounters showed us a solar system far more complex and dynamic than anyone had imagined. Jupiter, which we thought was a calm gas giant, turned out to be a world of extremes, with hundreds of violent storms, glowing auroras, and 3 previously unknown rings that are honestly more intricate than fine jewelry. Saturn's rings, once considered simple and few in number, revealed themselves as thousands of individual ringlets with braided structures that seemed to defy the laws of physics. Most shocking of all was the discovery of active volcanoes on Jupiter's moon Io and nitrogen geysers on Neptune's moon Triton, erupting at temperatures just 40 degrees above absolute zero. These findings totally shattered the idea that volcanic activity was unique to Earth and the inner planets. Maybe most significantly, Voyager 1 identified potential habitats for life on Europa and Enceladus, moons harboring vast liquid oceans beneath their icy surfaces. These discoveries transformed our understanding of where life might exist in the universe, expanding the concept of habitable zones way beyond traditional planetary boundaries. The mission's revelations keep influencing space exploration today, inspiring missions to study these potentially life-bearing worlds in much greater detail.
The eternal journey into galactic immortality.
In 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445, carrying humanity's golden record message to any intelligent civilization that might find it. Voyager 1's scientific mission may end in the late 2020s when its power finally fails. But honestly, its journey through the galaxy is just beginning. The spacecraft will keep traveling through interstellar space for millions of years, eventually becoming an artifact of human civilization drifting among the stars. In about 300 years, it'll enter the Oort cloud, a spherical shell of comets surrounding our solar system. After 30,000 more years, it'll completely escape the sun's gravitational influence and start orbiting the center of the Milky Way galaxy alongside billions of stars. The golden record attached to Voyager 1 contains sounds, images, and greetings from Earth in 55 languages, serving as a cosmic message in a bottle for any intelligent beings who might encounter it. This record includes everything from Bach's music to whale songs, from mathematical formulas to images of human faces. The spacecraft has become humanity's first interstellar ambassador, carrying our story into the cosmic deep. Long after human civilization has evolved beyond recognition, Voyager 1 will continue its silent journey through the galaxy, a testament to human curiosity and our drive to explore the unknown. The mission represents more than scientific achievement. It really embodies humanity's eternal quest to understand our place in the universe and reach beyond the boundaries of our cosmic home. From mysterious cosmic humming to impossible electronic survival, Voyager 1's 47-year journey has shown that our universe is far stranger and more dynamic than we ever imagined. This brave little spacecraft keeps rewriting the textbooks of space science while carrying humanity's message to the stars. If you're fascinated by these incredible cosmic discoveries and want to explore more mind-bending space mysteries, go ahead and hit that like button, share your thoughts about Voyager's amazing journey in the comments, and subscribe to Sci and Y for more adventures into the unknown. Thanks for watching. Keep exploring the cosmos.
A comet just erupted near the sun, and now a massive solar storm is racing to meet it on a collision course. In the next few weeks, Comet C/2025 R2 Swan will make its closest approach to Earth in recorded history, just as the sun unleashes its mightiest flare in months. This cosmic alignment is incredibly rare. We have a volatile comet, a powerful solar eruption, and a front-row seat from Earth. What happens when a solar storm meets a cosmic visitor? Let's explore this extraordinary scenario together.
First light, the outburst begins.
Comets are notoriously unpredictable, but what happened on September 26 caught everyone by surprise. Just 2 weeks after its closest pass to the Sun at a perihelion of 0.5 astronomical units, Comet Swan suddenly roared to life. Initially, it was a faint object, but amateur astronomers in Japan and Australia noticed a dramatic surge in brightness overnight. This wasn't a minor flicker. The comet's brightness leaped by a full magnitude, from 7.4 to a peak of 5.7, pushing it into naked-eye visibility under dark skies. What caused this? As the comet swung away from the Sun, intense solar heat penetrated its frozen nucleus. Pockets of sublimating cryovolatiles like frozen carbon monoxide and carbon dioxide buried for millennia reached their breaking point and exploded through the crust. This outburst ejected a massive cloud of gas and dust, dramatically expanding the comet's atmosphere, or coma, and feeding its enormous tail. According to cometary scientist Dr. Casey Liss of the Johns Hopkins Applied Physics Laboratory, such outbursts provide a rare glimpse into the primordial material from which our solar system was formed. This event signaled that Swan's inner engine was now exposed, making its next moves completely unpredictable, and turning it into a prime target for skywatchers worldwide. The sudden release of energy was so significant it altered the comet's light curve, deviating sharply from all predictive models.
Anatomy of a tail.
This isn't just a faint smudge in the sky. We're talking about a structure wider than 5 full moons laid end to end, stretching over 15 million kilometers through space. And its design tells a story. Comets actually have 2 distinct tails, and Swan's outburst put both on magnificent display. The first is the dust tail. It's broad, curved, and shines a pale yellow as it reflects sunlight. It's made of heavier micron-sized particles that are pushed gently by solar radiation pressure and tend to lag behind in the comet's orbit. The second, and more dramatic, is the ion tail. This tail is a narrow, straight ribbon of electric blue, composed of ionized gas like carbon monoxide ions, or CO+, which fluoresce brightly when excited by solar ultraviolet radiation. This glowing stream is blown directly away from the Sun by the solar wind at speeds exceeding 400 kilometers per second, acting like a cosmic windsock. As noted by comet expert Carl Battams of the U.S. Naval Research Laboratory, the ion tail is a perfect natural probe of interplanetary conditions. With Swan's tail now stretching across a huge patch of sky, it has become a perfect natural laboratory, exquisitely sensitive to the solar storm that is now heading its way.
The Sun awakens.
Just as the comet was putting on its show, the Sun, which had been quiet for weeks, decided to join the party with its most powerful eruption in months. On September 28, at 0843 Universal Time, satellites from the GOES network detected a massive spike in X-ray emissions, jumping from a background level of 10 to the -6 to 6.4 times 10 to the -5 watts per square meter. An M6.4 class solar flare had erupted from a magnetically complex sunspot group designated Active Region 4232, then rotating into view on the Sun's southeastern limb. M-class flares are the second strongest category, and a 6.4 is a significant event powerful enough to cause radio blackouts on the sunlit side of Earth. Scientists at NOAA's Space Weather Prediction Center, like lead forecaster Dr. Alexei Pevtsov, immediately began analyzing data from the Solar Dynamics Observatory's AIA instrument at multiple wavelengths, including 131 angstroms, to assess the flare's power and, more importantly, what it threw into space. The energy release was equivalent to millions of hydrogen bombs detonating simultaneously. The timing was incredible. Just 2 days after the comet's own eruption, the sun had fired a warning shot into the exact same quadrant of space.
Plasma on the move.
A flare is just the flash of light. The real power is in the billion-ton cloud of magnetized plasma it can hurl into space. And, this one wasn't aimed at us. Within minutes of the flare, coronagraphs aboard the SOHO spacecraft, specifically the LASCO C2 and C3 instruments, confirmed that a massive coronal mass ejection, or CME, had been launched. This wasn't just a puff of smoke. It was a colossal bubble of solar material and magnetic fields, with an estimated mass of 1 trillion kilograms, racing outwards at a staggering speed between 800 and 1,000 kilometers per second. Forecasters at NOAA's Space Weather Prediction Center, using the WSA-NLIL prediction model, quickly charted its trajectory. The verdict: Earth was in the clear, but the CME was barreling directly towards the region of space now occupied by Comet Swan and its magnificent sprawling tail. Solar physicist Dr. Angelos Vorlidas, a leading expert in CME imaging, confirmed the CME's broad 90-degree angular width made an encounter highly probable. A rare and potentially violent collision was now inevitable within 48 to 72 hours.
Magnetic scissors.
So, what happens when a comet's tail, which is a magnetic structure, meets a massive magnetic cloud from the sun? Sometimes things just snap. This phenomenon is called magnetic reconnection, and it's one of the most explosive processes in the solar system. A comet's ion tail is made of plasma, held together by magnetic field lines streaming away from the sun. A CME, however, is a tangled web of powerful magnetic fields, often containing a strong southward-pointing component, known as the Bez field. If this southward Bez field, with a strength potentially exceeding 20 nanoteslas, slams into the comet's oppositely directed magnetic field, they can't merge. Instead, they collide, break apart, and explosively reconnect into a new shape. As space plasma physicist Dr. James Drake has explained, this process converts magnetic energy into kinetic energy with incredible efficiency. When this happens, the energy release can be immense, acting like a pair of magnetic scissors that cleanly severs the entire ion tail from the comet's head. This is called a disconnection event, and it can happen in a matter of minutes, leaving the old tail to drift away as a new one begins to form.
The forecaster's puzzle.
Predicting this collision is more complex than it sounds. It's like trying to predict if one puff of smoke will hit another in a hurricane. While models from NOAA's Space Weather Prediction Center, like the NLIL heliospheric model, showed the CME's main lobe sweeping through Swan's sector, CMEs expand, twist, and deform as they travel hundreds of millions of kilometers through space. Hitting a relatively small target like a comet's tail is not a guarantee. The biggest challenge for forecasters is the lack of direct measurements. Since the CME is not aimed at Earth, we won't get in-situ data from satellites like the DSCO-VR spacecraft, which normally act as a warning system by sampling the solar wind a million miles upstream from us. Scientists must rely on images from spacecraft like SOHO and Stereo A to refine the CME's trajectory and predict the exact time of impact. An error of just a few degrees in the initial launch angle can result in a 10 million kilometer miss by the time it reaches the comet. The best estimates place the arrival between 48 and 72 hours after the flare. But the question remains, will it be a direct hit, a glancing blow, or a near miss?
Citizen science mobilizes.
When a cosmic event like this unfolds, the big observatories aren't the only ones watching. A global network of backyard astronomers becomes the front line. Professional telescopes have schedules booked months in advance, so they can't always drop everything to watch a single event. Citizen scientists, however, can provide continuous, round-the-clock coverage. This is crucial, because a tail disconnection event can be incredibly fast, unfolding in less than 2 hours. An amateur astronomer with a modest setup, like a 10-inch reflector and a modern CCD camera, could be the first person to capture the collision. Organizations like the Association of Lunar and Planetary Observers, or ALPO, have entire sections dedicated to coordinating comet observations. Renowned astrophotographer Damian Peach has shown how high-resolution amateur images can rival those from professional instruments. These observers are not just taking pretty pictures. They are collecting valuable scientific data, or photometry, that can be used to measure brightness changes and map the tail's structure with incredible detail, helping to build a global record of this rare encounter.
The perfect alignment.
As if a volatile comet and a perfectly aimed solar storm weren't enough, the celestial geometry for this event is almost unbelievable. On October 21, 2025, Comet Swan will make its closest approach to Earth, passing just 0.25 astronomical units, or 39 million kilometers away. That's roughly 100 times the distance to the Moon. For a comet with an orbital eccentricity of 0.98 and a low inclination, that's an exceptionally close flyby. This proximity makes it an easier target for even small telescopes. The timing is equally perfect, coinciding with a new moon, meaning the sky will be at its darkest. But there's more. On that same date, a hypothetical interstellar visitor, 3I Atlas, reaches a superior conjunction on the other side of the Sun. As orbital dynamicist Dr. Davide Farnocchia from NASA's Jet Propulsion Laboratory would note, the probability of a dynamically new comet like Swan and an interstellar object aligning so closely in time and space is vanishingly small. This alignment provides a unique chance to compare a native solar system body with an interstellar one under the same solar conditions, a rare convergence of a dynamic comet, a potent solar storm, and an ideal observation window from Earth.
Southern skies, spotlight.
For these crucial weeks, the best seats for this cosmic show are in the Southern Hemisphere. From major observatories like the Siding Spring Observatory in Australia, to backyard setups in South Africa and South America, Comet Swan will be high in the sky after sunset. Its path takes it through the southern constellations of Grus and Piscis Austrinus, passing near the bright guide star Fomalhaut. Viewers can use this star as a guidepost to locate the comet, which will appear as a fuzzy star with a long, faint streak extending from it. Even a standard pair of 7x50 binoculars will be enough to reveal the tail, stretching over 2.5 degrees, the width of 5 full moons. For those in the northern hemisphere, the view will improve throughout October as the comet climbs higher in the western sky after midnight. The checklist for observers is simple. Find a dark sky, use a star chart to locate the comet, and watch for any changes. By taking images every few minutes, observers can create time lapses that will reveal the tail's motion and any sudden disruptions caused by the solar wind in stunning detail.
Cosmic forces collide.
Here's the bottom line. We have a comet that has just undergone a massive outburst, making it unusually active and producing a large, dense tail. We have a powerful M6.4 flare that launched a CME racing directly towards it at nearly 1,000 kilometers per second. And we have a historically close and well-timed approach to Earth, giving us a perfect view. This sets up a documented encounter between a solar storm and a comet's ion tail, a phenomenon that could cause dramatic changes, with spectral analysis potentially showing Doppler shifts in ion velocities of up to 50 kilometers per second. It's important to be clear, as a scientist from a program like the NASA Comet Observation Database would emphasize, the comet's initial outburst and the solar flare are a coincidence. The sun did not cause the comet to erupt. However, this coincidence has created a rare opportunity for both professional and amateur observers to witness the powerful dynamics of our solar system in real time. The key results are still unfolding, written in gas and light across the night sky. A cosmic experiment for the entire world to watch. We are witnessing a truly unique cosmic alignment, a volatile comet, a powerful solar storm, and a front row seat from Earth. What will happen when the CME slams into Swan's tail is still unknown. Will it be a gentle ripple or a dramatic disconnection that severs the tail completely? The only way to find out is to look up. This is a rare opportunity for anyone with a pair of binoculars or a small telescope to contribute to a global science campaign. The universe is putting on a show, reminding us of the immense and unpredictable forces at play. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Sci and Why.